For the rest of this class, we're going to be focusing on partial differential equations, PDEs. Super exciting because most problems in science and engineering are a function of multiple variables. Position, where it's in 3 dimensions, x, y, z. It's a function of time. It could be a 4-dimensional temperature profile that we're trying to solve. And those equations are governed by a partial differential equation. And we've focused a lot on ODEs so far in this course, but now we're going to turn our attention to partial differential equations. And in particular, we spent the past week focusing on Fourier series and their application to, for example, image analysis. But now we're going to apply it to solutions to partial differential equations. And the PDE that we're going to focus on first is called the heat equation. And today we're going to derive the heat equation from first principles, sort of, using a balance law. Suppose we have a solid piece of material. The temperature inside this solid varies as a function of position x that runs from this position here towards the right. It can also be a function of time. Now let's suppose that this material was subjected to a hot reservoir on the left-hand side and a cold reservoir on the right-hand side. So there's going to be a transfer of heat from the left over towards the right. And that's going to be described using what's called a heat flux. And that's denoted by the letter Q. So there's heat flux coming in from the left, and of course, there's going to be heat leaving from the right boundary of the solid substrate into the cold reservoir. Now we'd like to do an energy balance on this material. But as opposed to doing the balance on the entire material, going from 0 all the way to the length L, we're going to do the balance on a thin shell. And that's what I've drawn in blue. I've created a little cross section shown right here, and I've cropped out a small little section, a shell of thickness dx. So this position right here on the left has position x. Over here on the right is x plus dx. So this shell has a thin volume of the area, A, which is the cross-sectional area, times the thickness of the shell, dx. We like to do an energy balance inside this thin shell. So for any balance law, it satisfies this universal relationship of in minus out plus generation equals accumulation. Let's write that down. This is a generic balance law that's true for momentum, mass, energy, species mass. In minus out plus generation equals accumulation. Now let's think first a little bit about this accumulation term on the right-hand side. We like to figure out how much energy accumulates inside this control volume of this thin shell as a function of time and position. So let's think a little bit about this accumulation term. Okay, so for this accumulation term, we want to first think about how does the energy inside this thin shell of volume A times dx change with respect to time? How much energy accumulates inside that volume as a function of time? So now from thermodynamics, we have this concept of the specific internal energy, U with a caret on top. Now that's the specific internal energy is equal to the internal energy per unit mass. Okay, so it's an intensive variable. So the accumulation over here on the right-hand side is simply the time rate of change of the internal energy inside that small shell of volume dV. So it's d by dt of the specific internal energy times the small differential mass element dm. Of course, in this particular case, we're assuming that there's a density, which is uniform, times the differential volume dV. So the differential mass can just simply be written as the density times the differential volume. Of course, the differential volume is just the cross-sectional area A times the differential dx. And therefore, we can substitute into here. And what we get ultimately is just like that. So all I've done here is to take the differential mass of the shell, which is rho times the cross-sectional area A times the thickness of the shell dx, plugged it into here. And I've taken out the area, which is constant for this material, the density, which is also constant. Strictly, it doesn't need to be. If the density were not constant, if the solid were varying density as a function of position and time, potentially due to a chemical reaction or due to thermal changes that changes the volume, then you can't take out this volume, this density automatically. But for now, let's do the easy case where the density is constant, so it comes outside this time derivative. If it doesn't, you need to do a separate mass balance on the solid, where you have an evolution equation for the density, and now you have a coupled equation of the energy balance coupled to the time rate of change of your mass, the density evolution inside your solid. But in this case, the density is homogeneous, which is a simple case. The density comes outside the time derivative. So all we have left is du hat over dt, the time rate of change of the internal energy, the specific internal energy inside the shell, and the slope of that with respect to time. Now, we can take this internal energy derivative and do a small little trick from thermodynamics. Okay, so I've just used the chain rule to take the time derivative of the internal energy and rewritten that as partial u hat, partial temperature, times partial temperature, partial time. This is just calculus using the chain rule. And the reason why we did that is because the first term, partial u hat, partial t, is the definition of the heat capacity. It is how much energy does it take to raise the temperature of this material by 1 degree Kelvin. Right? It's, again, a material property. It's unique to the specific material that you're dealing with. So it's a material property that will just come outside. And now we have something that might be useful. We have partial temperature, partial time. Because ultimately, the goal of this whole exercise is we like to come up with an evolution equation that tells us the temperature inside the solid as a function of position and time. That's our ultimate goal. We want to come up with the temperature profile of this solid material when it's exposed to a hot and cold reservoir as a function of position and time. Temperature is going to vary because near the boundaries, it's going to be hot, it's going to be cold. In the middle, it might be adjusting to some initial condition that it was subjected to. And so we want to come up with an evolution equation of the temperature. And we have our first indication that we're kind of there. We have the time rate of change of the temperature profile inside this material. So now rewriting the accumulation term, all we have is, what we get is this expression down here. So the accumulation term on the right-hand side of the balance is simply equal to the density of the material, the cross-sectional area, the thickness of the shell, dx, the heat capacity, times the temperature derivative with respect to time, not position. I made a typo here. This should be time. Partial t, partial time. Okay, so now let's erase everything over here. I'm just going to move this expression over here on the right-hand side. Okay, so what I've done is to take in the accumulation term that we just derived over here on the right-hand side. And now we have in minus out and generation of energy inside this small little slab. Now, for this particular case, we're doing the simple example where there are no sources of energy inside the shell. There could be, for example, an exothermic chemical reaction happening inside this material. It might be a polymer slab that's undergoing a chemical reaction that releases heat with end-chain radicalization that's thermodynamically exothermic, and it releases heat. In that case, you would need to include a generation term. It would be related to the chemical reaction happening inside the slab, and you'd have a separate equation for the actual chemical reaction happening, a conservation balance of the reactants and products. And so you have an energy balance coupled to a species mass balance for the reactants and the products. Okay? So you would have that case there. Another situation where you might have a generation of energy might be electrical wire or some kind of heat generator actually located inside the solid. If I had a thin, for example, wire that's electrically conductive, there is electricity running through that wire. Now it's dissipating heat through the copper wire, and therefore the solid material surrounding it would receive heat from that process. That'll again be another example of a source of energy inside this slab as a function of position and time. But in this case, we're going to do the example of the simplest possible example where there are no sources of energy inside the shell. This generation term, let's not worry about it. Okay, so now all we have are the heat coming in and heat coming out. So this is where the heat flux Q comes into play. So first, for our particular case, we have a position x and x plus dx. And of course, it needs to be multiplied by the cross-sectional area. And now we have our balance of the in minus out of energy through the form of a heat flux, which is proportional to how much surface area is present. Kind of makes sense. The bigger the cross-sectional area, the more energy that's being pumped in across that material. And that's going to be equal to how much energy is accumulated inside that small little shell as a function of time. Okay, so at this stage, we're pretty close. All we need to have is a relationship between Q, the heat flux, and the temperature profile T. So the moment we get that relationship, we will have a differential equation of the temperature profile as a function of position and time. So all we need is Q, the heat flux, as some function of the temperature. The moment we have that, we're all done. This is called a constitutive relationship, and it actually is an extremely current and active area of scientific and engineering research. Not so much in heat transfer, but more so in fluid mechanics. In fluid mechanics, there is a similar relationship that we need to obtain when you do a shell balance over a momentum balance. And what you get eventually at this stage is a relationship between the stress tensor and the velocity, or gradients of that velocity. And once you have a relationship between those two quantities, you close the equation. So this is sometimes called a closure. A constitutive relation, which relates the flux to the conserved quantity, is oftentimes a closure that we need to be able to actually solve the problem. And there are lots of different constitutive relations and closure relations out there. And like I said, this is a very current active area of research. In the case of heat transfer, there's a very famous and very accurate relationship between the heat flux and the temperature called Fourier's law of heat conduction. And I want to take a moment to describe in detail the Fourier's law of heat conduction as a separate aside. So let's take a look at that right now. Okay, a quick aside on Fourier's law of heat conduction. Now in Fourier's law, we have the heat flux Q, which has units of energy per area per time, is equal to the negative of the thermal conductivity, which is the material property that tells you how conductive the material is to energy, heat transfer, times the temperature gradient, which is just the derivative of the temperature with respect to the position x. Now, if you think about this relationship physically, it makes kind of sense. If I were to think about the heat transfer inside this room, and I have a temperature difference of this side of the room, which is very hot, this side of the room, which is very cold. So there's a temperature difference, and so there's a slope of the temperature, a temperature gradient from this side to this side. And the bigger the slope, right, the bigger the gradient, you would expect the more heat transfer you would get. That's proportional to how big that temperature difference is between this side and this side. That's why we have this term over here on the right, partial temperature, partial x. It's proportional to the gradient. The bigger the slope, the more heat transfer you have across that material. But you know that not all materials are created equal in terms of heat transfer. Some materials, like metal, stainless steel, just from your personal experience, you know that it conducts heat a lot better than other materials, like air. And therefore, there is a proportionality constant called the thermal conductivity that tells you how conductive that material is to heat. So the larger the thermal conductivity, the more conductive that material is to heat and energy transfer. And finally, there's a negative sign out in front because of the sign convention. If I have a temperature gradient coming from here to here, there's going to be a negative temperature gradient coming in this direction, and therefore the sign convention of the heat flux vector is it goes positive and it goes down a temperature gradient. That's why it's negative of partial T, partial X. Now, some textbooks, and especially in thermodynamics, they have a different sign convention. It's either the work done or the work taken out by the system, or the heat put into the system or heat taken out by the system. Depending on which sign convention you adopt, sometimes this negative is not present. But in the way I describe it, it's always going to be the heat is going to go down a temperature gradient. Okay, so now some of you might be wondering, why is the heat flux proportional to, linearly proportional to the gradient of the temperature? Well, it turns out that I put quotes around a law because it really isn't strictly a law. It's an empirical guess. We made it up. We just guessed, or Fourier just guessed, that the heat flux must be proportional to the temperature gradient, linearly. But in reality, that doesn't have to be true. And in fact, it's often not true. In some materials, the heat flux is not proportional linearly to the temperature gradient. You might get higher order gradients, like the second derivative to come out, or it might be nonlinear function dependencies of the temperature gradient, the temperature, or higher gradients of the temperature. So this relationship, called Fourier's law, is not really a law. When I think of law, I think of conservation of mass, conservation of energy, of momentum. Those are laws. Those are always obeyed. In contrast, with this kind of relationship, which is an empirical guess, it's not really a law. So I have kind of a problem with the way a lot of textbooks say it's a law. It's not really a law. It's an empirical relationship that happens to be true in many materials. It turns out this relationship works perfectly well for most materials that you'll encounter as a scientist and engineer. But some cases, it doesn't satisfy. This relationship doesn't apply very nicely. So in general, it could be any arbitrary function that relates the heat flux to the temperature or the temperature and its gradients. And so more generally, this type of relationship is called a constitutive relation. So it's more accurate to say Fourier's constitutive relation. And in fact, in other areas of transport phenomena, like momentum transfer and mass transfer, this relationship often isn't linear. A great example is in fluid mechanics. There are lots of materials that are behaving as a viscoelastic or non-Newtonian material. And the constitutive relation, which relates the stress tensor to the velocity gradients, aren't just a linear relationship. In a linear relationship, it's called Newtonian fluids or Newtonian constitutive relation. But in many situations, the foods you eat, the foams you put on your body, the sunscreen, various sorts of consumer products, they don't behave in this linear fashion. And so this is a situation where many materials have a nonlinear relationship between the flux vector and the quantity that's conserved. Okay, so now one more comment about Fourier's constitutive relation. I wanted to talk a little bit about the thermal conductivity because it tells you something about the material properties of the system. It tells you how conductive that material is to heat. Now, when you think about the thermal conductivity, intuitively you know that metals and certain materials have a large thermal conductivity. So let me just write down a couple of thermal conductivities and we'll talk about them. Okay, so here are common values of the thermal conductivity for different types of materials. For metals, as you would imagine, it has a very large thermal conductivity, hundreds of watts per meter Kelvin. Those are the units of thermal conductivity. Okay, so hundreds. That kind of makes sense. On a cold day, you touch that stainless steel outside of the chain-linked fence or any metal, it's very cold. It's very cold to the touch. Okay, so that kind of makes sense. For glasses and ceramics, the value is much lower. I wrote the value for glasses here. The thermal conductivity is about a single watt per meter Kelvin. And there's a very famous and popular class of glass called fiberglass. And this one has a very unique property in the sense that the thermal conductivity is a very small value. It's on the order of 0.01 watts per meter Kelvin. And this is in part the reason why fiber optics and fiberglass are so popular in various applications in science and engineering. Not only because they can bend light, but because you want the thermal conductivity to be poor. You don't want it to heat up easily as it passes through light, because that would interfere with a lot of its applications. So the fact that it's close to being an insulator, the fact that it's a very poor conductor of heat, actually makes this material very valuable. So that's why fiberglass, this is one reason why it's a very popular and heavily used material in science and engineering. Its thermal conductivity is way lower than many other common materials. Now, one of the most important materials in all of life is air, in part for this property. The thermal conductivity is extremely low, 0.02 watts per meter Kelvin. And this is the reason why we have double pane windows. For those of you watching this, living in a very, very cold climate in the winter, or not even in the winter, year round, if it's cold there, you know that you have double pane windows. When you go into a big building or a shopping center, there's a big, thick piece of glass, and then a gap of just stagnant air, and then another piece of glass on the other side. And you know this is a very thick composite of glass, air, and glass. And the reason why it's designed that way is because air has a very, very low thermal conductivity. We want the cool air temperature outside to stay there and not conduct heat across the walls of the building. And therefore, you leave a big, thick gap of air. Same thing with airplanes. When you sit on the window side seat, you notice that the window is extremely thick because there's an air gap between the two windows from the outside to the inside, and that it takes advantage of the very low thermal conductivity of air. In a more close example, a lot of you wear, and I wear as well, the puffy jackets, the North Face Thermoballs, the Nanopuff Patagonia jackets, the thin piece of cloth with down or cotton with another thin piece of cloth. All it's doing is it's trapping pieces of air close to your body. And the idea is that your body is warm, it will quickly warm up the air between your body and the outside, and it traps that stagnant air close to your body, and it keeps you warm, it keeps you insulated. And so that's why those jackets are so effective, is because it's trapping a little bit of air between your body and the outside. So you're paying $300 to $400 to keep fancy air close to your body. That's effectively what you're doing with those types of jackets. Okay, so the final aside I wanted to talk about with the thermal conductivity is something you might notice when you go on the kitchen tile. When you're walking around in your home and you walk from the carpet to the kitchen tile, all of a sudden it feels cooler all of a sudden. You were fine on the carpet walking barefooted, but the moment you walk onto the kitchen tile, all of a sudden it feels cold. And the reason why is not because the temperature is lower, right? The temperature is the same on the carpet and on the kitchen tile. The difference is that the thermal conductivity is different between the carpet and the kitchen tile. And because our body perceives the heat flux, that's what matters. It's not really the temperature gradient between your warm body and the floor that's making the difference. It's, in this case, the thermal conductivity difference. The thermal conductivity of the carpet is much, much lower than the thermal conductivity of tile. And therefore, even though the temperature difference is the same, your foot is still at 37, the carpet's at 25 C, it's still the same partial T, partial X, but the K, the thermal conductivity, is different between the two materials. And that's why the kitchen tile feels cooler. Okay, so let's go back to the rest of our derivation. This is what I wanted to talk about with regard to Fourier's law of conduction or Fourier's constitutive relation, and an aside on the thermal conductivity. We just saw that according to the Fourier's constitutive relation, the heat flux is related to the temperature by a linear relationship of the temperature gradient and the thermal conductivity. Let's write that down. And like we just saw during the aside, this is kind of like the simplest possible constitutive relation that one could use. It says that the heat flux is proportional to how steep that temperature profile is. And this type of linear relationship is sometimes called Hooke's law, like the spring that you learned in high school, F equals to negative K times delta X. How much you pull the spring, the recoil is proportional linearly to the displacement about its equilibrium spring position. It's the same thing here. It's Hooke's law. And that's true for solid mechanics, fluid mechanics, heat transfer, mass transfer. This type of linear relationship between the flux and the conserved quantity, when it's linear, is called Hooke's relationship or Hooke's law. So this is an example of Hooke's law. All right, so let's use this constitutive relationship to finish this problem. Now all we need to do is to plug this form in to our in minus out fluxes equal to accumulation, and in a couple of steps we will have driven the heat equation. Okay, so what I've done is to plug in Fourier's constitutive relation into the flux heat in, heat flux out, and then kept the accumulation term on the right-hand side. Notice that I've crossed out the cross-sectional area A on both sides of the equations, and therefore the area no longer appears here. Okay, what I'm going to do now is to divide the small little increment shell thickness dx element from the right-hand side over to the left. I'm also going to divide through by the density rho times the heat capacity CV and factor out the K. Now let's simplify this a little bit. Okay, so all I've done is just a little bit of algebra. I've brought over the material properties over onto the left-hand side. I've also divided through by the small increment dx. Now, what's the stuff inside this bracket? Derivative of the temperature with respect to position at the right-hand boundary of the shell minus the left-hand boundary divided by the small little increment dx. Now, think back to your very first calculus class when you learned that the definition of the derivative is the value of a function at some position, x plus dx, minus the volume of the function at position x divided by dx. So as you make dx smaller and smaller and smaller, you're making the shell thinner and thinner and thinner until it reaches a continuum point. And once they reach that small little thin shell, it becomes the definition of the derivative. So all this is just a definition of the derivative. So this is nothing more than the second partial derivative of your temperature with respect to position. So there we have it. We have a combination of some material property over here on the left-hand side times the second derivative with respect to position equals the right-hand side, the first time derivative of your temperature. So our initial goal of trying to come up with a temperature profile, an evolution equation for how the temperature varies inside the solid as a function of position and time, can be obtained by solving this governing equation. Now, one last point, a lot of times people will write this combination of terms as a material property called the thermal diffusivity. It's got units of meters squared per second, and it is a measurement of how diffusive energy and heat is across that material. It's similar in concept to the thermal conductivity. Of course, you can tell here it's linearly proportional to the thermal diffusivity. So you can think of it as the same. How conductive, how easily does energy or heat transmit across that material? That's what the thermal diffusivity indicates. Now let's clean it up and write the final expression at the very end. Okay, So what we've done is just rewrite what we've derived using in minus out plus generation equal accumulation into this final form. This top equation is the 1D heat equation, which tells you how the temperature varies inside of a 1D material, like in this case a solid, as a function of the time t and the position x. Now, of course, we don't live in a 1D world, we live in a 3-dimensional world. So it turns out one could repeat the exact same calculation in 3D, not just over one direction, but over x, y, and z, using the exact same argument. And you will come up with the 3-dimensional version of the derivation we just made. And the only change we need to make is that on the right-hand side, you don't have not only a second derivative with respect to position x, but you also have a second derivative with respect to position y and z. And that can compactly be written in the form of what's called a Laplacian. And depending on different coordinate systems, the Laplacian will take on different forms, but morally, it's the same. You have a second derivative with respect to each of your individual coordinates, x, y, and z. So now, there we have it. We have our governing equation of the heat equation that we derived from a balance law of the shell balance. Now, from next time, we'll start solving this equation and using our knowledge of the Fourier series to make a lot of progress on solving heat transfer problems in a finite domain.